Okay, so how is everyone today? Good, I hope? All right. It's Friday, that's good. So next Friday we're having a quiz. So again, we have quizzes every other Friday. That's nice. But no quiz today. Okay, so the YouTube channel, I posted a link to it last night. Good. I'm not going to write. I'm not going to make any more messages about it. Good. Any questions about that? All right. So then here we go with math. The 25th. So we've been talking about arithmetic operations, add, which is the same thing that you know and love from grade school, and then multiply, again, the same thing you know and love from grade school, but maybe it wasn't stressed very hard that what multiplication actually is it's doing add over and over again. That's what it's doing. Repeated addition. And then if you say, oh, really, add, really, multiply is repeated add, then you might say, well, what if I do repeated multiply? And we talked about that, and what is it that you get if you do repeated multiply? Exponents, right? And then, you know, we end the conversation there, more or less, and say, you know, but we did say, what if you do repeated exponent? Do you get something? And the answer is, yeah, you do. You get something. But we don't talk about it in our class. Okay, good. So, you know, add, multiply, exponent. They form a sequence of operations there. Fine. One thing to note about add and multiply is that add, addition, is commutative, which means that if you've got a bunch of things and you're adding them all together, you can sort them into whatever order that you like. Sort them how you want. Same with multiplies. So if you've got a bunch of things all multiplied together, then you can sort them into whatever order that you want, in the sense that 3 multiply 5 is the same as 5 multiply 3. So you can commute them. Moreover, add and multiply are associative, which is to say that if you've got 3 or more things that are all being added, so like maybe you've got 50 things and they're all being added together, then you can put parentheses anywhere that you want. And effectively what that means is that even though the order of operations says that you need to do the leftmost add first, in fact, because addition is associative, you can do any of the ones first. And the final result is not going to be any different. Same with multiply. But exponent doesn't have either one of these things. Right? So exponent is not commutative, and exponent is not associative. So in the following kind of sense, so then first, so exponent is not commutative. It's not commutative because a exponent b is not the same as b exponent a, and you could write this as, you know, a to b like that, not the same as b to a. And you need to understand this this not equal. This means generally, which is to say for every a and b. So it might be true for like your favorite a and b. So if you chose a is 1 and b is 1, okay, then it's true. But it's not true generally, because you know, for example, what's 2 to 3?
8.
That's 8. Whereas what's 3 to 2?
9.
That's 9. So it's not permitted that you can reverse them. Whereas 2 plus 3 is the same as 3 plus 2, and 2 multiply 3 is the same as 3 multiply 2. So exponent is not commutative, and also last time we discussed that exponent is not associative. So we did that last time. And what we said is that in our class is that it's going to be an error. It's an error to write this, A to B to C. So it's not permitted that you should do that. Rather, you need to put the parentheses wherever it is that you intend for them to be. So you must write one of. So you must use one of. So if you want that one to occur first, then you write A to B to C. But if you wanted the other one to occur first, then you write A to B to C. Okay, good. Any questions about this? All right. So you got to keep that in mind when you're dealing with that. Now, another thing that we said last time, the very end of last time, is that we were talking about inverses. So a summary of what we said last time at the end was, something like this. So in two columns, I'll say, so we have add, and in the other column, multiply. So, A and B are called additive inverses when A plus B is 0. And then saying this in an overly stressed way, I could say that A and B are called additive inverses when it is the case that you add them and you get the additive identity. All right? So then over here, in this column, I could say A and B are called multiplicative. That should say not that. This should say A and B are called additive inverses when that. And then A and B are called multiplicative inverses when A multiplied by B is 1. And again, to say this in an overly stressed way, A and B are called multiplicative inverses when it is the case that you multiply them and the result is the multiplicative identity. All right? So now the reason, one reason to do this is so that you can see the parallel structure. But also, as a matter of foreshadowing, later in the course we're going to talk about functions, and you can add, subtract, multiply, and divide functions just like you can do that with numbers. But there's a further thing you can do with functions that you don't do with numbers, and this new thing that you do with functions is called compose. And at that time, we're going to say exactly the same thing, except there's going to be 3 columns. And the third one is going to say that 2 functions are said to be compositional inverses when it is the case that you compose them and you get the compositional identity. Okay, and then it's even more interesting than that, because it will turn out that function composition doesn't commute. It means that it matters what order you do it in. So then you'll have to say that in fact 2 functions are compositional inverses when you compose them in this order and you get the identity, and you compose them in the other order and you also get the identity. All right, that's just a matter of foreshadowing. Any question about this? All right. To that end, now we have a formula. So the formula for additive inverse, its name is called negation. X becomes negative x. So the additive inverse of 5 is negative 5. The additive inverse of negative 8 is negative 8, which you would probably just say as 8. Fine. The formula for multiplicative inverse is also common enough to have its own name. It's called reciprocal. So its formula is that x, the reciprocal of x is 1 over x. Reciprocal. And now, we want to ask which numbers have an additive inverse. So which x in the reals have an additive inverse? Okay, so then you should know the answer to the question. So which ones do?
All non-zero.
So in this case, it's just all of them. Okay, so then what you said is this one. So which x in the reals? Which of them have an additive inverse? So to confirm that 0 has an additive inverse, is there a number that you can add to 0 so that you'll get 0? 0. Okay, so then over here the question is which x in the reals have an additive inverse? Translating that into a math question, it's asking you're asking, when can we solve this equation? So when can we solve for y? In this equation, x plus y equal 0. So under what circumstances can you solve for y? All circumstances, right? What do you need to do? Well, you can subtract x, right, from both sides. So if you subtract x from the left-hand side, then what's the result? Just y. And what will be the right-hand side? Negative x. So strictly speaking, I put this bit here about the formula first, sort of just for your convenience, but really, logically, it belongs after this. Because first you have to ask the question, when can you do it? The answer to the question is all the time because of this, and as a result, the formula is negative x. But, okay. So, as a result of this, we can do this always, and so we can say, therefore, every x in the reals has an additive inverse. All right. Analogous question over here. Which x in the reals have a multiplicative inverse? Okay. So just like we translated that question into something about an equation, we want to do that now. So the question is still, when can we solve for y? So when can we solve for y? And what is the corresponding equation? So instead of x plus y is 0, what do we have?
X times y equals 1.
Yeah, we have x multiply y is 1. Okay, now, so to proceed from here, we said, yeah, if we want to solve for y, then what I'll do is I'll subtract x from both sides. Now, what would we want to do here? Yeah, so instead of subtracting x, we want to divide by x. Okay, now, so we want to divide by x, both sides. But it's not always okay to do that. So for example, it's completely fine to divide by 2, both sides, no problem. It's completely fine to divide by 22, both sides, or 22 million. It's fine to divide by -2, both sides. All that's fine. But there is an x for which it is just not fine. 0, right? It's not permitted that you should divide both sides by 0. So this is only possible when x is not 0. So in that case, the answer would be that y is 1 over x. But notice the equation 0 multiplied by y equal to 1. What y can you plug in so that the equation will be true? How about 2? What if you plug in y as 2? It would read 0 multiplied by 2 is 1. Well, 0 multiplied by 2 is 0, so that would be false. And if you wrote if you made y like 1,000,000, then 1,000,000 times 0 would still be 0. There isn't a y you can plug in that'd make it work. The fact that this has no solution is the reason why you can't divide by 0. That's the reason why. It's not because, like Miss Harris said in 4th grade. It's because this equation has no solution. Good. Any question about all this? All right. So a typical question, exercise, is something like this. So confirm or deny. Each pair is, and then 2 parts. So first, confirm or deny each pair is an additive inverse, additive inverses. So the first pair we'll ask about is how about 3 and 5. 4 and negative 4, 0 and 0. All right. So the way that you do this to check if 2 numbers are additive inverses, what do? You don't subtract them. You got to add them. Got to add them. And so I'll do that. So 3 plus 5 is 8. So I'm not asking like a complicated arithmetic thing here. But now, how do we answer the question of whether or not these are additive inverses?
They are not.
Okay, so I agree that they're not, but why are they not? Right. Because this, what we got, is not 0. So not 0. Therefore, 3 and 5 are not additive inverses. So again, I'm not testing whether or not, I'm not testing if you can do 3 plus 5. Okay, that's not what's being asked here. It's asking if you understand that what it means to ask if 2 numbers are additive inverses, what it means. It's saying add them and then check if you get the additive identity. It's carrying out the procedure that's being tested. All right, so about this one?
Yes.
Okay, it's going to be yes. So the way we're going to do it, we're going to say, okay, we'll do 4 and then plus negative 4. So we add them. And the result is 0. So, that's 0. We got a 0. So therefore, 4 and negative 4 are additive inverses. All right. How about here? So now it's again going to be yes. I gave you 2 numbers. Okay, so they will add them together. So 0 plus 0 is, well, 0. So that's a 0. And therefore, you could say it like this. You could say 0 is its own additive inverse. That's interesting. Okay, so then that was the first question. So the second question is now, instead of checking if they're additive inverses, please check if they're multiplicative inverses. So how about 2/3 and 3/4, 4 and negative 4, and negative 13 over 14, and negative 14 over 13. All right. So, you know, what do we have to do? Multiply. So 2/3 multiply 3/4. So we're multiplying them because we're asking if they're multiplicative inverses. So that's why we're multiplying them. So, you know, using the powers of arithmetic that you learned in Miss Harris's class, you can see, oh yeah, the 3's cancel. So I'll do just a little bit and say, okay, the 3's cancel, and then I have 2/4 there, and then I can do that, so that's half. Okay, half. Okay, so we did it. Now, what's the answer to the question? So the answer is going to be to observe that that is not 1, which is to say the multiplicative identity. So therefore those numbers 2/3 and 3/4 are not multiplicative inverses. All right, 4 and negative 4. Oh yeah, those are inverses, right? Yeah, we just showed that, right? So if you caught someone making that error, what would you say to them?
We're doing multiplicative inverses, so we have to multiply instead of add.
Right. Okay, so can you see it? So the question of inverse depends on what you're doing. Right? It depends on what kind of thing you're doing. So if you're doing add, okay, then there's an additive inverse, and if you're doing multiply, there's multiplicative inverse. Okay, so we multiply them together, you get 16. So what we got is not 1. And therefore those numbers 4 and negative 4 are not multiplicative inverses. So even though they're additive inverses, that doesn't mean that they're multiplicative inverses. Okay, so for this one, negative 13 over 14, and then multiply by negative 14 over 13. So, you know, we want to simplify this. I'll do it in a couple steps. So in the first place, I noticed that we're multiplying two negative numbers, which means that the negatives cancel. So I can drop the negatives. So the negatives get dropped, and then this could be written as 13 over 14, and then multiply 14 over 13. And then I can look at that and say, oh, look, the 13s cancel and the 14s cancel, and then what do I have left? Just 1. So, you know, we got 1. And therefore, those numbers, negative 13 over 14 and negative 14 over 13, are multiplicative inverses. Any question about this? So again, this is a little tedious. I don't dispute that. But what's being tested is not whether or not you can add two numbers or multiply two numbers. That's not what's being tested. What's being tested is, do you understand the machinery of arguing in this way, to say that what does it mean to check if two numbers are multiplicative inverses? It means to multiply them and then ask, did I get the multiplicative identity? Because later in the semester, the question is going to be, here are two functions. Are these compositional inverses? Then what you will do is you will compose them and check and see if you get the compositional identity. And then, you know, if multiplying two numbers and checking if you get the multiplicative identity takes up that much room. But then when you're doing the same thing with functions and composition, then it takes the whole page. So I need you to be comfortable with doing this in this tiny little thing so that you understand, oh yeah, doing it with functions is the same thing, it's just more work. Any question about it? All right. Good. So one of the things that we said last time is we've said a lot of stuff about exponents and things like that, but we went for a long period of time where all of the exponents were non-negative, so we didn't have any negative exponents, but now we want to have negative exponents. So we start out by defining that x to negative 1 means 1 divided by x. So x to negative 1 is the multiplicative inverse of x. So of course this only works when x is non-zero. 0 to negative 1 is not defined. Similarly, x to negative n is 1 over x to regular n, like that. Now, last time, we said that x to m multiplied by x to n could be written in a simplified way. So how do you write it? How does it simplify? So x and then what? M plus n. Because this is a counting issue. What this is, x to m, that's just a convenient way to say that that's a group of x's. There's m of them in there, and they're all multiplied. So if you had a desire, you could write all of them out. X, m of them. And then here's another group of x's, and there's n of them in there, and they're all multiplied. So here, there's m x's all multiplied together, and here's n x's all multiplied together, and those things are in turn multiplied together. So what this is this just one long string of x's all multiplied together. And then how many of them are there? Well, that many. This is just the math way to say the thing that Miss Harris said in fourth grade, or first grade, where she said, Sally has 10 apples, and then Bruce comes along and he has 7 apples, and then all together they have 17 apples. That's what that's saying. Okay, so now we want to consider this similar thing, except now we want to write x to m divided by x to n. So now we want to do that. So it's very similar thing, except I changed the multiply to a divide. Okay, so I'm going to leave myself a box here where I'll write the answer, and let's sort of explore and figure out what should be the answer. So I realize that some of you probably already know the answer right now, but there's some loose ends that I find every time I teach this course. I need to tie this up before we proceed. All right. So then how about x to, 7 divide by x to 3? Let's try and figure out what this could mean. So that's going to be a fraction, and in the numerator there's going to be a group of 7x's all multiplied together, and in the denominator there's going to be a group of 3x's all multiplied together. So you could write it like this. So 1, 2, 3, 4, 5, 6, 7 in the numerator, and in the denominator 1, 2, 3. And then looking at it like this, you can see, oh hey, I've seen this kind of thing before. There'll be some cancellation. So you could pair up some stuff and say, well, those cancel, so those are gone, and then these cancel, and those are gone, and then this pair cancels, so those are gone, and now I've run out of x's in the denominator anyway, so I can't continue this procedure any further. So the result will be a fraction like this, and then I can see that there's 4 x's left in the numerator, so I'll write that down. I'll write x, 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 x like that. But there's no x's left in the denominator, so what am I supposed to write? 1? Okay. So I'll note that there was a little bit of hesitation, so we're going to come back to that. So the answer, it is 1. The answer is 1, but I'll note that there was a slight hesitation, I think. Okay, so then, dividing by 1 is the same is a nothing. It's doing nothing. And then the most compact way to write that is x to 4. Okay, so there's really, I think, no surprises here. Okay, because really this is just the grade school question of, you know, Sally has 7 apples, and then Bruce borrows 3 apples from Sally, and then how many apples does Sally have? 4, right? So it's not really super complicated, but you need to also be able to handle this kind of case. So w to 5, say, divide by w to 8. Okay, we want to simplify this one also. So here, again, using the same strategy, I'll say that there's, you know, this is a group of 5 w's all multiplied together in the numerator. And then in the denominator, that's a group of 8 w's all multiplied together. And then, oh, look, they pair up, you know. So I'll do the pairing, you know, those cancel, those are going to cancel, those cancel, these cancel. And then, you know, now I've run out. I ran out of stuff to cancel. So the result is going to be a fraction. So the denominator, I can see that there would be 3 w's left over. Because, you know, I can see that there's 3 more. And now what I'm going to write is incorrect. So if you're copying, you know, what I'm writing, please carefully note that what I'm going to write is incorrect. So here is one of the most common errors that I see from students at this point. And I don't know, I have a theory about why it happens, but I don't know exactly why. But all right, so there's 3 w's down there, so I write those, and then, oh look, I ran out of w's, so I'm going to write a 0. So this is incorrect. Okay. Now, an easy question to answer, if you know what you're doing, is to say, okay, if that's not right, then what is the right answer? Okay, 1. So I agree entirely that is the correct way to proceed. Okay, so then putting that on pause for a second, the question about that. Then I'll say, okay, w, the shortest way to write that is w cubed. And then if the instructions say that you have to write your answer without any divisions and no fractions and things like that, then how could you write this without any divisions or fractions or what have you? W to negative 3. Fine. So again, this is exactly the same thing as before. So now it's Sally has 5 apples, and then Bruce comes by and borrows 8 apples, and so as a result, Sally has negative 3 apples. And if there's too much cognitive strain saying negative 3 apples, okay, then you could say Sally has $5 in her bank account, and then makes an $8 purchase, and now she is $3 overdrawn, or something like that. So, you know, that being the case, what is the formula up here?
X to the power of n minus n.
Right. That many apples, take away that many apples. All right. Fine. So now I want to come back to this, because every time I teach this class, this comes up. All right. So now, in this part, I'm going to write something that is a different problem, but it's similar enough that I think that you may see what I'm getting at. Okay. So I'm going to write. How about w plus 2 subtract w plus 5. And that'll be enough. So I'll say it like that. So there's an expression. All right. So now I'm going to make it all adds by saying this. I'm going to say that this is w plus 2, and then instead of saying subtract w, I'm going to say plus negative w, which is a little clumsy, but you know, I can say that. The only reason is that now that it's all adds, that means that I'm in the clear to commute them into the order that I want. I can sort them how I like. So I'm going to do that. So then it will read as w plus negative w, and then plus 2 plus 5. All right. So the 2 plus 5, you know, I can do that. I'm practically an expert at that. So that'd be plus 7. And now, concerning the w's. Do you observe that the w's cancel?
Yes.
Okay, good. Now, because the w's cancel, that means that I write the thing every time things cancel, I write the thing that I always write. So the w's cancel, so I'm going to write 1. Okay, so, all right, so then that's not right. So here's an easy question. So if I'm not supposed to write 1, then what am I supposed to write?
The identity.
I'm supposed to write 0. And then now, here's where I'm gonna complain. I'm gonna say, look, you just told me that when I cancel, I'm supposed to write 1, and now you tell me that when I'm canceling, I'm supposed to write 0, and I'm just gonna throw my hands up in despair. Okay. What's the distinction? Right. So look at the two groups of operations. In this group, in this one, we're doing multiplies and divides. And in this group, we're doing adds and subtracts. You can have cancellation with regard to adds and in regard to multiplies and divides, and you can have cancellations in regard to adds and subtracts. A cancellation when you're doing multiplies and divides results in what? 1, because that is the multiplicative identity. And a cancellation when you're doing adds and subtracts results in 0, because that is the additive identity. And if you were doing some other thing, if you were doing bananas, you know, if you were doing, you know, banana and undo banana, in the sense that multiply and divide, you could call divide, undo, multiply. If you had bananas and unbananas, then a cancellation would result in the banana identity. Okay. So, you know, this, we have to have the multiplicative identity, and here we have to have the additive identity. And if that's not enough, then I'll remind you that our definition of w to 5, when we defined it on the very first day, we said what that means is make a group of 5 w's and multiply them all together. And we wrote something like this. We didn't make it all the way down to 5, but we wrote something like this. So w, 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 like that. But in fact, when we, then we were in a place like this, and I said, well, what about w to 4? And then we said, oh, make 4 w's. And then what about 3? And then we kept going. And then I asked about, well, what about 0 w's? And then we had a little bit of a problem. Right? Because if you add w to 0, that means make no w's. And then multiply them all together. But if that's all that you say, then you don't have anything on the right-hand side of the equation. So notice that the horizontal space on either side of the equation is uneven. And that's totally not my style. So evidently, I'm probably going to write something there. So what do I write there? A 1. Because w to exponent 5 means take a 1, take 5 w's, multiply them all together. That's what it means. So right here, there is an implied 1. So can you see it? So all those cancel, and that is what is left. That 1. All right. So now I need to address something, and that is that I take teaching very seriously, and I also take math very seriously. And I know that there's 50 minutes, and basically, as far as I'm concerned, I have to account for every one of them, and they're all precious. Y'all are paying for a service, so that's from y'all's point of view, and from my point of view, I am like an idealist. And I've just spent like the last 8 minutes talking about this. And that's because this is not the first time I've taught this course, and this thing is really important, and I watch students miss it every time. Okay? So can you see it? All right. Any question about it? Okay. Good. So Looks like I'm missing something. Nope. So now we have shift. So multiplication by 10 is called a right shift. So that's kind of a weird name for multiplication by 10. But multiplication by 10 is called right shift. And the reason why it's called that is because of the following. That if you take some number, like 1.314, and you multiply it by 10, then what is the result of multiplying by 10? Right, so the answer is going to be 13.14. Yeah, the point is going to shift. It's going to move one position to the right. It's going to move past one digit. Okay, so the result is 13.14. So the fact that the point moves one position to the right is why it's called a right shift. Okay. Now, generally speaking, when you have a given any number, you know, like I don't know, like 20.19, like that, you know. Any real number can be written thusly, and there's a part that's to the left and a part that's to the right. So the part that's to the left of the point, this is called the integer part. Integer part. And the part that's to the right is called the fractional part. Okay. So now that being said, I'm going to write down one more, which is kind of easy to overlook and misunderstand. So how about this number? How about 2019? So just 2019, not point. Notice that this number, of course, it is a number. What's its integer part?
2019.
Right. And then what's its fractional part? Right, it's zeros, right? So it's not there. So then if I say 2019 multiplied by 10, like that, it can be kind of confusing to see why it's still called a right shift. But the reason why it's called a right shift is because, after all, isn't it the case that 2019 can be written in this way, 2019.0? Okay, so this isn't deep or anything, but I just need to point it out. So, all right, then that moves like that. So then it would be 2019, and then with a trailing 0. Okay, good. Any question about that? Right shift? So, you know, anytime someone says an adjective thing, right? So if I say like a red shift, then you should think, well, is there like a green shift or something? So the fact that there's a right shift, you know, you should have no surprise when the very next thing I say is a left shift. So what is gonna cause a left shift? Divide by 10, or multiply by 1/10. Okay, but I'm going to say divide by 10. So this is called a left shift. Because, you know, if you take a number, 1.314, and then you divide by 10, then now the point moves, and it's going to move to the left. So it moves to the left, and the result, you in some sense could write 0.1314, but you know, you can write an integer without a fractional part, but you know, you can't write a fractional part without an integer part, which means that what do I need to write right here? A 0. Okay. Any question about this? Okay. So these are called left and right shifts. Now the thing is that you can do multiple shifts. You can do like shift to the right 8 places, or shift to the left 8 places, whatever you want. And moreover, you should be advised that we count in base 10. Okay. And essentially every culture that exists currently in the world counts in base 10, except for some minor groups of people, like uncontacted peoples, that live in like the Amazon. They don't necessarily count in base 10, but essentially all the folks who use computers and print paper and stuff like that, they all count in base 10. Why do we all count in base 10? Because we have 10 fingers. That's it. It's not more complicated than that. There's nothing special about 10. And, the fact that we have 10 is entirely just an evolutionary circumstance of history. It's a contingent matter. If we ever meet aliens and they have 8 fingers, then they're probably going to count in base 8. And our machines, our computers that we make, all that they do is they just do arithmetic really quickly. And they don't count in base 10. They count in base 2. Because it was easier to make machines that count in that base. So the reason why I'm saying this is that if you were counting in base 8, then a right shift would not be multiplied by 10. It'd be multiplied by 8. And for a computer, a right shift is not multiplied by 8 or 10. It's multiplied by 2. Okay? So, to that end, I'd like for you to observe the following. So suppose we have this number, 131.4. And suppose that I wanted it to be the case that observe that the integer part has 3 digits, 131. Now, suppose I wanted it to come to pass that the integer part had just one non-zero digit. So it would be fine for the number to read 1 point whatever, 2 point whatever, 3 point whatever, 4 point whatever, all the way up to 9 point whatever, but not 0 point whatever. That's not going to be okay. So I want essentially to shift that point to be there. All right. So here's what I'm going to do. I'm going to say, here's this number, 131.4. And then to cause a left shift, I need to divide by 10. But I can't just, what I've written right now is not true, right? Because this number is not the same as itself divided by 10. Dividing by 10, that does something. So I need to also undo it. I need to say, well, I'm going to sort of do and undo the same thing. So what's the undo for divide by 10? Multiply by 10. So what I've written here, this is a fancy way to say do nothing. Okay? But what I'm going to do is I'm going to eat up that divide, but leave the multiply there, so that the result looks like this. So that it looks like 13.14, and then multiply 10. So now, do I have the point in the place that I said I wanted it? No, right? Because I wanted it to be the case that there was one non-zero digit to the left of the point. Currently, there's 2. So if the trick worked once, it'll work again. So 13.14. And then I'll say divide by 10, and then I've got to undo that, multiply by 10, and I have to not forget that other multiply 10 that already was there. So again, this is a fancy way to say nothing. So I'll do it. And now the result is 1.314, and then multiply 10, multiply 10. And then, isn't there a nicer way to say multiply 10, multiply 10? Well, yes, but I want a different one.
Like 10 squared.
10 squared is the one I was fishing for. So 1.314 multiplied by 10 squared. So now, you can achieve this state of affairs with any number that you start with. It might be that you start with this number, you need to shift the point to the left. It might be that you start with something like 0.00 blah blah blah, something like that, and you need to shift the point to the right, but you can always achieve this circumstance. So this circumstance, where you have a number like this, and there's exactly one non-zero digit to the left of the point, and then you've got multiplied by 10 to some exponent, like 2 or -8 or what have you, that's called scientific notation. And we're going to talk about it a little more next time. But here's the reason why you want to do it, is that in chemistry and physics and other places, you deal with numbers that are inconveniently big or inconveniently small. So if you wanted to write them out, I mean to say. So an example of a number that's inconveniently big is Avogadro's number. Avogadro's number is the number of hydrogen atoms it would take to have 1 gram of hydrogen. If it was the most common isotope of hydrogen. So what is Avogadro's number? Can you remember? 6.0 what? 6.022, and then what? Times 10 to 23. Now that's a lot. But to be clear, if you wanted to write that without the 10 thingy, then you'd have to shift the point to the right 23 places. So we'd shift it past the 022, 6022, and then now I have to write 20 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that's Avogadro's number. And then the only thing to ask is that which one of these ways is more convenient. That one? Okay, so have a nice weekend.